Section: Introduction. In this section, we will discuss the challenges faced by large language models, LLMs, and how retrieval augmentation can help improve their performance. LLMs have shown great potential in solving various tasks but often struggle with hallucination, especially when dealing with less common knowledge. Retrieval augmentation combines information retrieval and nearest neighbor search to enhance reasoning with LLMs. This approach helps reduce the generation of unsupported content. However, the effectiveness of retrieval augmented language models, RALMs, can vary. One common method, in-context retrieval augmentation, RA, involves adding retrieved content to the input to guide the LM's output. While this can help, it does not always ensure accurate information attribution. Another approach, such as 10-number-10 modifies the LM's output based on nearest neighbor matches in a corpus. This method provides more direct attribution but may lower the quality of text generation. Additionally, retrieval augmentation can slow down the generation process due to the time needed for retrieval and expanding the LM's context. To address these challenges, we introduce NEA Neighbor Speculative Decoding, NEST, a new approach that enhances the quality and speed of text generation. NEST builds upon the 10-number-10 method by incorporating real-world text spans into the LM's output. It includes a passage retrieval step at the beginning to improve search efficiency. NEST operates in three main steps during content generation. 1. Conance-based interpolation. This step uses a relative retrieval conance (RRC) score to adjust the LM's output based on token retrieval uncertainty. 2. Dynamic span selection. Inspired by the copy generator, COG, NEST selects not only the best token but also extends to a span in the corpus when retrieval confidence is high. 3. Relaxed speculative decoding. NEST evaluates selected spans based on probability mixture, accepting only highly likely prefixes. NEST outperforms base LMs and standard 10-number-10 in various tasks like question answering and text completion. It also competes well with in-context retrieval augmentation on different datasets. By combining approaches, NEST enhances generation quality and attribution. Moreover, NEST significantly speeds up long-form generation without sacrificing quality. Section Summary. In this section, we introduce the concept of large language models, LLMs, and their common issue of generating inaccurate content known as hallucination, especially when dealing with less common knowledge. To tackle this problem, retrieval augmentation combines information retrieval and nearest neighbor search to enhance LLM's reasoning abilities. Our proposed NEA Neighbor Speculative Decoding, NEST, approach improves content generation by dynamically selecting text spans and adapting the LM's output based on token retrieval results, leading to enhanced performance in various tasks like question answering and text completion, even outperforming standard methods like in-context retrieval augmentation. Section: Probability Interpolation. In this section, we work on probability interpolation. During our inference process, our language model gives us a distribution of tokens along with a hidden state. We use this hidden state as a query to search a data store and find the nearest neighbors based on similarity. The final distribution is calculated using a softmax function over the similarities of all the retrieved neighbors. We introduce an inverse temperature parameter to adjust the distribution. We use this parameter practically, where the dimension of the hidden state is considered. This process is akin to how attention is computed in the transformer model. For measuring similarity, we use the negative squared distance metric. Tokens that are not found in the retrieved neighbors are given a probability of 0 based on an indicator function. Moving on to the two-stage 10NN search, we acknowledge that maintaining a token-level key-value store can be costly in terms of both time and storage. To strike a balance between speed and accuracy, we implement a two-stage approach commonly used in information retrieval systems. In the first stage, we divide the documents in our corpus into smaller passages and use a hybrid retrieval system to select relevant passages efficiently. In the second stage, after obtaining the top retrieved passages, we encode the prefixes of all tokens using the language model's encoder to create a key value store on the go. We then search for the nearest neighbors based on similarity using the hidden state as queries. This two-stage design helps us balance search speed and accuracy, with the passage-level index being much more efficient than the token-level index. We also introduce confidence-based output interpolation, where we combine the language model's distribution and a non-parametric distribution using a coefficient. This coefficient is computed based on the token retrieval score, incorporating a sigmoid function to adjust uncertainty. This method, called relative retrieval confidence, is particularly useful for generation tasks. Additionally, we discuss dynamic span selection, where we extend the context of sampled tokens to maintain coherence in the generated output. We use a max pooling strategy to select the starting token of the context, ensuring consistency in the generated text. Furthermore, we explore relaxed speculative decoding to adaptively control the length of generated spans. By introducing a relaxation factor, we can adjust the acceptance probability of tokens in a span, allowing for more flexibility in the generation process. This approach helps in generating coherent and varied text outputs. Section Summary. In this section, we describe the process of probability interpolation in our language model. During inference, we use the hidden state as a query to retrieve nearest neighbors from a data store based on similarity, computing a non-parametric distribution using a softmax function. We also implement a two-stage design for efficient token search, balancing latency and accuracy by first retrieving relevant passages and then searching for nearest neighbors within those passages. Section: Experiments. In this section, we assess nest and various baseline models across different tasks such as text completion, question answering, fact verification, and multi-choice tasks to understand how factual, fluent, and properly attributed nest is in different domains. Our focus is on evaluating models that follow instructions accurately. We use Llama 2 Chat in a zero-shot setting, where we exclude the few-shot demonstrations from the instructions to mimic real-world model usage. For text completion, we utilize benchmark datasets like Wikitext 103, which consists of verified Wikipedia articles, and Pile of Law, a dataset of legal and administrative data. We split the test data into validation and test sets. We measure language modeling performance using perplexity scores and assess free-form generation using metrics like Rouge 1, Rouge 2, L, and MAV. In question answering, we work with knowledge-intensive datasets such as natural questions, NQ, trivia QA, TQA, hotpot QA, HQA, and med-MCQA, MQA. Since we remove in-context demonstrations for free-form generation, we use answer-level recall, hit at 1, to check if the output contains any correct answers rather than exact matches. For fact verification, we evaluate tasks like biography generation and truthful QA, a benchmark for detecting false beliefs. We use fact score for biographies and a method that compares the similarity of model outputs to true and false reference answers for Blue and Rouge 1 in truthful QA. In closed set tasks, we use the Massive Multitask Language Understanding (MMLU) benchmark covering various subjects and report macro accuracy for each domain. We rely on knowledge sources such as Wikipedia and Pile of Law for different tasks. Wikipedia's 2021 dump is used for most tasks, while Pile of Law data from Hugging Face is specifically used for text completion on legal content. In the inference setting, both 10NNLM and Nest share a retriever in the first stage. We encode segments using DRAGON+ and BM25 into dense and sparse vectors, respectively. By querying both indexes simultaneously, we retrieve top passages and combine similarity scores before selecting the final passages. We also incorporate raw and nest methods for better results. For evaluation, we set specific parameters like token lengths for different tasks and tune hyperparameters on dev sets of relevant datasets. Baseline models and Nest share the same hyperparameters for all tasks, with a focus on perplexity and generation metrics. We evaluate publicly available instruction-tuned language models, specifically the Llama 2 chat series with varying model sizes. Additionally, we apply the two-stage strategy to 10NLLM and utilize in-context retrieval augmentation, RAW, by adding retrieved evidence into the prompt without refreshing passages frequently. Section Summary. In this section, we conduct experiments to assess Nest and other models across various tasks like text completion, question answering, fact verification, and multi-choice tasks, focusing on evaluating instruction following models. We use Llama 2 chat in a zero-shot setting by removing few-shot demonstrations to mimic real-world model usage, reporting metrics like perplexity for language modeling and Rouge 1, 2, L, and Mauve for free-form generation. Additionally, we evaluate NEST's performance on knowledge-intensive question-answering datasets, fact verification tasks, closed-set tasks, and utilize Wikipedia and Pile of Law as knowledge sources for different experiments. Section: Main Results. In this section, we present the main results of our Nest model compared to other baselines. We found that for language modeling tasks on Wikitext 103 and Pile of Law, raw Nest has the lowest complexity. When it comes to text completion, raw achieves the best Mauve and Rouge scores on Wikitext 103, while raw Nest performs better for 7B and 13B models on Pile of Law. We noticed that for legal documents, directly quoting clauses from the source is more effective than using information from Wikipedia. In question-answering tasks, raw Nest tends to work better for smaller models like 7B and 13B. The performance gap between base language models and other methods decreases for larger models like 70B, which aligns with previous findings that retrieval methods are more beneficial for smaller models. For fact verification tasks, Nest outperforms base language models but falls behind raw in terms of FACT-SCORE. However, raw Nest surpasses raw for the 70B model. The decrease in performance for raw 70B is due to generating shorter claims, which is penalized by the FACT-SCORE metric. In the truthful QA dataset, semi-parametric language models consistently outperform base models and ROS, as in-context retrieval seems to negatively impact scores. Nest, on the other hand, interpolates results at the output level and performs better in such cases. The combination of raw Nest is also influenced by in-context retrieval. In closed-set tasks, Nest performs similarly to raw, while raw Nest achieves the best macro scores on AV. Overall, Nest outperforms base language models and 10NLLMs on most tasks and is on par with raw. Combining raw and Nest further enhances performance on certain tasks. Despite the modest improvements, Nest offers better attribution and latency, as we will discuss in the following sections. To improve latency in LLM generation, we utilize dynamic span selection and relaxed speculative decoding, allowing for quick draft proposals and processing multiple tokens simultaneously. Our experiments on a Nest 70B model show that even with additional retrieval overheads, the slowest Nest model is faster than the base LM, demonstrating the effectiveness of span selection and speculative decoding. By tuning the relaxation factor, we can achieve a balance between latency and accuracy. Fetching longer spans from the corpus reduces generation latency per query. The sweet spot for both low latency and high accuracy is around a certain relaxation factor. An important feature of Nest is providing attribution at a span level, ensuring accurate references directly from the corpus. This span-level attribution is more precise and granular compared to baselines, with the ratio of tokens traceable back to the corpus ranging from 33.2% to 95.5%. Consistent attribution is achieved by having consecutive segments from the same source, with the average length of spans from the corpus varying from 3.0 to 27.9 tokens. This feature enhances attribution accuracy in LLM generation. Section Summary. In this section, we present the main results of our NEST model compared to other baselines. Our raw NEST model achieves the lowest complexity for language modeling on Wikitext 103 and Pile of Law datasets, excelling in text completion tasks. We observe that for legal documents, quoting exact clauses is more effective than Wikipedia, and raw NEST performs better for smaller question answering models. Section: Retrieval Augmentation. In this section, we explore retrieval augmentation, which involves using external knowledge sources to enhance the performance of language models on tasks that require a lot of knowledge. We introduce DRQA, a model that combines extractive methods and independent retrievers for answering questions in a wide range of topics. Other works like Realm, RAG, and Atlas have also integrated retrieval techniques into pre-training and fine-tuning for tasks that require a lot of knowledge. These approaches can be categorized into three groups. 1. Input augmentation. Methods like replug and in-context realm suggest adding retrieved passages at the beginning of prompts to provide factual support without prior training. Self-RAG introduces special tokens for adaptive retrieval and uses different critics to improve the output of realm. 2. Intermediate fusion. Retro uses a unique attention mechanism to include multiple pre-processed text fragments in intermediate layers for better integration of retrieved information. This method has been successful with larger decoder-only language models, as shown by Retro++ and Instruct Retro. FID also uses an encoder-decoder structure in a zero-shot way to achieve better performance at a document level. 3. Output integration. NLLM proposes blending the retrieval distribution with the language model's prediction. Other methods suggest training adaptive interpolation techniques involving training and fine-tuning excessively. Some approaches joint train the phrase encoder and language model to dynamically expand the vocabulary using retrieved phrases, such as copy generator. In terms of inference time revision, speculative decoding is a method that uses a small model to generate drafts quickly for a larger model to evaluate, improving latency. REST suggests drawing multiple drafts from a data store and using a prefix tree to compute the proposal distribution. This method falls under unbiased self-revision. Previous work on fact-checking also follows a similar idea of generating factually consistent texts with evidence through post-hoc editing, like Fruit and Peer. RARR introduces more complex planning with language models to verify evidence and create attribution reports. However, there are limitations to these methods. While they can retrieve segments from a corpus and use them in generation, errors may still occur depending on the accuracy of passage retrieval and token retrieval. Additionally, without further fine-tuning, the integrated system may not perform optimally and could benefit from fine-tuning on specific tasks. Semi-parametric language models may not enhance in-context learning, as prompts may not align with the database content. Current neural retrievers may struggle with processing in-context few-shot information, requiring techniques like query reformulation for better understanding.